Hello, ladies and gentlemen. My name is Andrew Elshaw, and I'm a student of Central Queensland University and work for the Cairns Regional Council. My final year engineering project has been supported by my academic supervisors, Professor Masood Khan and Dr. Nur Hassan, and my industry supervisor, John Bishop, from the Cairns Regional Council. My project was looking at optimising the submersible mixes within a wastewater treatment plant bioreactor. The Cairns Regional Council currently operates 3 wastewater treatment plants. However, the focus of this project is the Northern Wastewater Treatment Plant, located north of Cairns Airport. The plant is designed for an average dry weather flow of 22.5 million litres per day, with a maximum flow rate of 1,300 litres per second, which is 5 times the average dry weather flow. The cost of operating the facility has increased. The monthly electricity costs in 2015 were $54,000, which is up from $52,000 in 2014. The main treatment component of the wastewater treatment plant is the bioreactor. A bioreactor is a compartmentalized structure where biological reactions occur, resulting in the removal of nitrogen and phosphorus compounds. Without this process, discharging wastewater into rivers or the ocean would be detrimental to marine life and/or promote the growth of algae. The Northern Wastewater Treatment Plant is an activated sludge process and consists of several anoxic, anaerobic, and aerobic zones. The bioreactor has 3 25 kilowatt VSD pumps and 8 7.6 kilowatt submersible mixers. Anoxic Zone 1 contains all 3 VSD pumps and 1 7.6 kilowatt mixer. The Anoxic Zone 1 is the focus of this project. The aim of the project is to determine the optimal configuration for submersible mixers within the Anoxic Zone. This will be achieved by developing a computation fluid dynamic model of the Anoxic Zone using Anson software. The results of the project may lead to a reduction in electricity consumption, and this would result in financial savings to Council. As previously mentioned, Council operates another facility of similar configuration, so the outcomes of this project may be implemented beyond this project. Lastly, it will allow for a better understanding of the hydrodynamic performance of the bioreactor. One of the key factors that influences the performance of a bioreactor is the velocity of the fluid. If the velocity is too low, this may result in settlement of microorganisms, which would be detrimental to the bioreactor's ability to break down nitrogen and phosphorus compounds. The requirements of velocity for activated sludge processes have been extensively researched by the wastewater industry. It is recommended that a minimum velocity of 0.3 meters per second be achieved. The specific power dispensation of the Anoxic Zone can be calculated mathematically from the dynamic viscosity of the fluid and the determined suspended solids per cubic meter. Literature recommends a range of 8 watts per cubic meter up to 13 watts per cubic meter. If the specific power was too low, this may indicate that settlement could be occurring, and if the value is too high, this may indicate that the Anoxic Zone is wasting energy. The shown image is of the Northern Wastewater Treatment Plant, and denoted is the Anoxic Zone 1. The Anoxic Zone is 8.1 meters wide, 13.7 meters long, and 5.8 meters deep. The first phase of the project was to develop a 2-dimensional computation fluid dynamic model and determine a suitable turbulent equation to proceed with, while also completing a mesh-independent study. The CFD model was created in Anson using their design modeler. Once the geometry of the model was constructed, it was then imported into the meshing platform of Anson. The initial model was constructed with the default meshing options, and then the mesh was refined. Once the model had its mesh, it was then imported into Fluent, where the boundary conditions were defined, and then the simulation was commenced, with the results being recorded. The 3D model used the same approach. However, the major difference was the solution controls implemented for the two different models. The 2D model was simulated using steady and simple approach, whereas the three-dimensional model used transient and coupled. The reason the solution controls were adjusted for the 3D model was to decrease the time required to achieve the solution controls. Two sets of velocity readings were taken. The preliminary data was used to validate the initial two-dimensional model and was collected at the inlet, bend, dead spot, and outlet. These locations are shown on the image to the right. Velocity readings for the preliminary data were taken 0.5 meters off the wall and at a depth of 1 meter normal to the wall surface. The velocity probe uses an electromagnetic sensor to measure the velocity in one direction. For the extensive data collection, velocity readings were collected using the same equipment and taken in the same 4 locations. Readings were collected at the surface and at 1 meter intervals below the surface down to 3 meters. Readings were collected parallel and normal to the wall surface. The velocity was observed and the minimum and maximum readings recorded. Suspended solids were also collected in the same 4 locations and at 1 meter intervals below the surface. The results were recorded. Additional physical samples were also collected and tested in the laboratory. The physical samples were used to validate the probe readings. 3 different turbulent equations were simulated to determine a suitable equation to proceed with. 3 turbulent equations were K epsilon standard, K epsilon realizable, and K omega standard. From the simulation results, the CFD velocities were compared to the average velocities observed from the preliminary data. The results from the K omega simulation differed by 3 up to 10%, whereas the K epsilon standard differed by 6 up to 100%, and the K epsilon realizable differed by 0 up to 300%. However, for the realizable model, the velocities in 3 of the 4 locations were closer than the K epsilon standard model. These results were aligned with the statement from literature that K omega will produce more accurate results than K epsilon equations. As previously stated, a mesh-independent study was required to ensure the size of the mesh was not influencing the results. Anson Fluid used the approach called finite volume method, where the geometry is divided into controlled volumes where partial differential equations are solved. Therefore, as the number of nodes and elements are increased, the results of the partial differential equations should only marginally differ. Iteration D of the two-dimensional model had 160,000 nodes and elements, and is denoted by the light blue line. As shown by the image on the right, the black line that denotes iteration E of 250,000 nodes and elements is in close agreement with iteration D. Therefore, the results only marginally differ, and therefore increasing the number of nodes and elements by 90,000 only slightly changes the peak exit velocity. The velocity of the fluid was plotted against the curvature length of the outlet to complete a mesh-independent study. The simulation is of iteration E for the K omega standard model. This is a top view of the zone with the inlet in the bottom left-hand corner. The outlet is in the top right corner, and the A-recycle pump is adjacent to the inlet and along the bottom edge. The mixer has been neglected from the simulation to evaluate the hydrodynamic performance without its influence. The flow from the A-recycle pump is prominent through the zone, and it can be seen that its curvature towards the outlet is influenced by the flow from the inlet. Additionally, a swirl entrailment from the A-recycle pump propagates for the duration it takes for full flow to be achieved, which is approximately 3,000 iterations at steady and simple. The swirl entrailment that propagates from the A-recycle pump to the outlet results in the region experiencing a velocity around 0.3 meters per second. The region in the top left-hand corner, where the submersible mixer is located, is subject to velocities below 0.3 meters per second, and therefore settlement of microorganisms may occur in the region, which may result in undesirable biological conditions. The relationship between velocity and pressure assists to illustrate regions within the noxic zone that may achieve the desired velocity and why. Velocity is inversely proportional to pressure. In regions where the velocity is higher compared to other regions in the zone, the static pressure is lower. And where static pressure is higher compared to other regions in the zone, the velocity is lower. The velocity vector diagram on the right provides further information on the flow pattern within the zone. From the flow between the aerocycle pump and the outlet, a vortex is created. Furthermore, short-circuiting may be occurring in this zone. This would be undesirable as it could reduce the contact time between the microorganisms and the nitrogen and phosphorus compounds. The image shown is of the three-dimensional model with a completed mesh. The inlets into the zone are coloured blue and the outlets are coloured red. There are two types of inlets for the anoxic zone 1. The inlet and the aerocycle pump, of which there are 3. The flow from the inlet is from the return activated sludge pump, or otherwise known as MRAS, and the daily inflow into the plant. The flow rate gives a velocity of 0.149 meters per second. The inlet has a 3.5 meter by 2.7 meter opening and a 0.8 meter by 3.5 meter opening. The outlet, denoted in red, has the same dimensions as the inlet. However, the configuration is reversed. The larger outlet is on the bottom and the smaller outlet is on top. This was done to assist with mixing. The zone has 3 aerocycle pumps. From left to right, they are numbered 1 to 3. The aerocycle pumps are all duty, and an even runtime is managed to ensure even wear. During the collection of physical data, aerocycle pump was operating. The flow rate from the aerocycle pump resulted in a velocity of 0.832 meters per second. The three-dimensional model underwent 3 iterations of mesh refinement. Iteration A had 4,500 nodes and 22,000 elements. Iteration B had 16,900 nodes and 90,000 elements. Iteration C had 240,000 nodes and 1.3 million elements, and took 70 hours to simulate. It was assumed that as the two-dimensional model achieved mesh independence at 250,000 nodes, at 240,000 nodes for the three-dimensional model, mesh independence was also achieved. This could be investigated further with additional time. The image is of the isosurface plot for velocities of 0.15 meters per second and greater. Therefore, the results from iteration C suggest that much of the anoxic zone is below the recommended velocity. Furthermore, the three-dimensional model highlights the limitations of two-dimensional modelling, in that the vertical clearance between features cannot be considered. For this project, the vertical clearance between the top inlet and the aerocycle pump results in a different flow pattern to that observed from the two-dimensional model. The flow from the aerocycle pump continues to the opposite wall and is not curved towards the outlet as a result of the inlet flow. The only region within the anoxic zone that experiences a velocity of 0.3 meters per second is within the path of the aerocycle pump. The following images are in the Z-X plane, which is the top view of the anoxic zone. Velocity vectors are shown for depths of 1 meter, 3 meter, and 5.13 meters, which is at the aerocycle pump level. The 1 meter and 3 meter depth velocity vectors illustrate how the flow through the inlet behaves and how the bend influences the flow pattern. The velocity around the bend can be observed to be the highest and most prominent for the 1 meter and 3 meter depth velocity plots. Furthermore, the flow after the bend from the inlet can be seen to decrease in magnitude and produces a vortex. This is vastly different from the two-dimensional model plots. Furthermore, the region in the top right-hand corner, where the mixer is located, While still subject to low velocities, the flow direction is upwards, and this may assist to keep microorganisms suspended. This, however, is due to the flow from the A-recycle pump. From the velocity vector, the region in front of A-recycle pump 3 may accumulate sediment, and this is better illustrated from the velocity vectors in the YZ plane. The two images are of the velocity vectors in the YZ plane in front of A-recycle pump 1 and pump 3. These images illustrate the expected flow direction and magnitude. Considering the left image for A-recycle pump 1, the flow within the path of the pump is able to achieve the desired velocity, which results in a flow deflecting off the opposite wall, with some of the flow travelling upwards to the surface. At a middle depth, and at 1/3 and 2/3 of the length along the zone, the velocity vectors indicate to potential stagnation points within the zone. Considering the right image for A-recycle pump 3, towards the right of the image, the flow can be observed to be low and in the downwards direction. Therefore, it is expected that settlement of microorganisms would occur in this region. However, if pump 3 was operational, this would overcome the low velocity in this region. The streamlined path plot again provides further details on the expected hydrodynamic performance of the anoxic zone. The simulation shows that above the path of the A-recycle pump and through the middle zone, the velocity is less than desired. The streamlined path plot also highlights regions from the zone that may be subject to settlement, and therefore where undesirable biological conditions could occur. Furthermore, the flow seems to move directly towards the larger outlet, which suggests that short-circuiting is occurring. There was a number of velocity readings which were within 15% to the physical data, as shown. However, of the 72 velocity readings collected, 53 readings of the physical data were below the CFD model. Therefore, the CFD model is typically producing velocity values higher than the physical data. This may be due to the simplifications and assumptions invoked for the CFD model. The suspended solids were recorded for the 4 locations and at depths of 1 meter below the surface down to 3 meters. The cable length for the probe was only 4 meters, and this limited the depth of reading. Extrapolating the suspended solid results out to consider the full depth of the zone, the difference in concentration for the inlet is 12%, 21% for the bend, 32% for the dead spot, and 13% for the outlet. The recommendation criteria for determining if good mixing is being achieved is a difference of 10% between the top and the bottom of the zone. Therefore, 2 locations are marginally outside this criteria, while the bend and the dead spot differences would indicate that good mixing is not being achieved. From the suspended solid readings, the specific power ranges from 8.2 watts per cubic meter to 8.9 watts per cubic meter, and this is towards the lower side of the recommendation. Highlighted from the computational fluid dynamic modelling was the limitation of 2D modelling compared to 3-dimensional modelling. Neglecting the vertical clearance between features produces unrealistic outcomes. Also, the 2-dimensional model neglects one component of the resultant velocity, and this too influences the flow pattern. Therefore, as computational power has significantly increased, it would be strongly recommended to undertake 3-dimensional modelling, as it is able to illustrate the true hydrodynamic performance. Of the 3 turbulent equations used, K omega standard more closely aligned with the physical data collected from the treatment plant. Further improvements may be made by investigating other turbulent equations which were not investigated during this project. From the CFD modelling results, short-circuiting may be occurring from the inlet. The influence of this could be better understood if a CFD model was developed that included all 4 anoxic zones, and if data on suspended solids were collected throughout the zone. The use of submersible mixers may not be required by increasing the flow rate from either the MRAS pump or the A-Recycle pump. It is again recommended to extend the CFD model to include all of the anoxic zones to better understand how the increased flow rate performs within each zone. I would like to take this opportunity to acknowledge the support and guidance of those who have assisted me with my project, whom without this project would have been much more challenging. Professor Masood Khan and Dr. Nur Hassan of Central Queensland University, and John Bishop and the treatment staff at the Northern Wastewater Treatment Plant, and Cairns Regional Council. Thank you very much for your time today.